So you type a question into your favorite AI tool, like something really straightforward.
All right.
You hit enter. And then you just wait. The cursor blinks, the little loading animation spins. I mean, maybe 10, 20, even 30 seconds go by where the model is quote-unquote thinking before it even types a single word.
Yeah, we have definitely all been there recently, staring at our screens.
Exactly. Just wondering why these massive, incredibly advanced neural networks suddenly seem to be taking forever to answer the most basic queries.
It's a universal frustration right now, for sure, because as models have gotten smarter, they have also gotten significantly slower and honestly much more expensive to run.
Right, which brings us to today's topic. Because you, the listener, are feeling the direct effects of what researchers are actually calling the verbosity tax.
The verbosity tax, I really love that term.
It fits perfectly. Anyway, welcome to the Deep Dive. We are thrilled to have you here in the studio with us today. Just think of yourself as the third person pulling up a chair to our conversation.
Glad to have you here.
Our mission today is to look right under the hood of modern generative AI. We want to figure out why this verbosity tax is happening, and more importantly, how it's being fixed.
Because it is being fixed.
It is. We have a stack of sources in front of us, and they're anchored by a state-of-the-art research paper. It's titled LEAD. Length-efficient adaptive and dynamic reasoning for large language models.
It's a bit of a mouthful.
Total mouthful, yeah. But we are going to explore how researchers are using the concepts in this paper to teach AI to be fast, cheap, and smart, all at the same exact time.
And honestly, this is arguably the most critical engineering challenge in artificial intelligence today.
You really think it's the biggest one?
Oh, absolutely. I mean, we are at a point where the most advanced reasoning models are practically penalizing you, the user, for their own intelligence.
That's a great way to put it.
Yeah, they are chewing through massive amounts of compute power, draining battery life on local devices, and just eating up context window budgets simply because they cannot stop over-explaining everything.
So to understand the solution in this lead paper, I feel like we first need to look at why these AI models suddenly started talking so much in the first place.
Right, the root cause.
Based on the background in our sources, this all traces back to how the newest generation of models, so like OpenAI 1 and DeepSeek R1, how they were actually trained.
Yes, the training methodology changed.
They rely heavily on something called chain of thought prompting, combined with reinforcement learning.
Correct. So over the past couple of years, the prevailing training method has been to reward an AI purely for getting the final answer right.
Makes sense. You want the right answer.
You do. But the reinforcement learning algorithms basically taught these models a very brute force survival rule, which is think longer to think better.
Think longer to think better.
Exactly. The models realize that if they generate more intermediate steps, if they just spell out every single tiny logical leap, they're statistically way more likely to arrive at the correct final output.
Okay, let's unpack this. It's almost like asking someone, hey, what time is it? And instead of just looking at their wrist and saying, it's 2 p.m., they give you a multi-page dissertation.
Yes.
They walk you through the mechanical history of the pendulum clock, give you this whole analysis of daylight saving time, maybe offer a philosophical musing on the nature of seconds, and then finally they say, it's 2 p.m.
That is exactly what is happening. The model has entirely decoupled the length of its response from the actual complexity of the task you gave it.
Because it just knows that talking more equals a better chance of being right.
Precisely. Now, if you are asking an AI to solve a graduate-level Olympiad math problem, you absolutely want it to show its work.
Right, I'd expect a long answer for that.
A problem like that legitimately requires thousands of tokens of reasoning. But the AI is applying that exact same massive computational brain power to, like, simple arithmetic.
Which is incredibly annoying. For you and me, that means waiting a minute for an answer that really should take 2 seconds.
And for the companies running these models, it means astronomical server costs. Every single word or token in AI generates costs electricity.
So the obvious question becomes, how do we constrain this? How do you teach an AI to be concise without accidentally destroying its ability to reason through the complex problems?
Right, because you don't want to make it dumber just to make it faster.
Exactly. My immediate thought is just to step in and give the AI a strict word count. Like, write a rule that says, solve this math problem, but do it in under 1,000 words.
Just a hard cap.
Yeah. If you go over, you fail.
Yeah.
Why can't we just enforce a hard limit like that?
On paper, that makes perfect sense. But in practice, researchers found that standard length penalties and static length controls are just fundamentally broken.
Really? Why?
It comes down to a structural pathology in how AI models update their behavior during training. Normally, researchers try to add an efficiency reward alongside the correctness reward.
So the AI gets a point for being mathematically right and another point for being short.
Exactly. But the problem is how those two rewards are actually combined. Historically, they use static weights, meaning they mix the correctness score and the efficiency score together on a fixed ratio before feeding that signal back to the AI.
And according to the LAAD paper, mixing them like that leads to something called reward collapse.
Reward collapse, yes?
I want to walk through this because the mechanics here are fascinating. The correctness reward is binary, right? You are either right or you are wrong, a 1 or a 0.
Yep, it's absolute.
But the length reward is continuous. It varies wildly. You could be 10 words under the limit or, 5,000 words over the limit.
Exactly. And in machine learning, whenever you mix a binary signal with a highly variable continuous signal using a static ratio, the higher variance signal just completely dominates the learning process.
The length signal drowns out the math signal.
Entirely. The model's optimizer, which is the mechanism that actually updates the AI's internal wiring, it just loses track of what actually matters.
Okay, let's ground this in a hypothetical.
Hmm.
Imagine the AI is trying to solve an algebra equation during training, and it generates 10 different attempts.
Okay, let's say all 10 attempts get the math perfectly right, but they all vary wildly in length.
Right.
Because they all got the math right, the correctness variance is 0. There is no difference between them on the accuracy scale.
So they all look identical in terms of being correct.
Exactly. So the only signal the AI actually sees is the length penalty. The AI aggressively updates its wiring to be shorter and shorter. It forcefully compresses its reasoning.
Which sounds good until, wait, what if it gets the math completely wrong?
This is where the collapse happens.
Wow.
If all 10 attempts get the math completely wrong, the correctness variance is still 0. So the length penalty still drives the update.
Oh.
Yeah. The AI actually learns to be concise about its totally incorrect math. It gets rewarded for confidently giving you the wrong answer as long as it does it quickly.
That is wild. Okay, hearing this, my instinct as a programmer would just be to write an if-then script, like a manual schedule.
How do you mean?
Well, if the AI is struggling, turn off the length penalty. Tell the AI, hey, focus purely on correctness for the first 100 training steps so you learn how to do the math.
Okay.
And then once you're getting the right answers consistently, I'll flip a switch and tell you to focus on being concise. Why do we need a complex new framework if a human can just schedule the shift?
Because a manual schedule completely ignores the heterogeneity of the problems. Think about the data set the AI is training on.
It's huge, right?
Massive. It contains basic addition and it contains advanced calculus. A single global schedule cannot remain appropriate for both of those at the same time.
Because it learns them at completely different rates.
Precisely. If you apply a global budget or a global schedule, you force a compromise. Let's say you enforce a global budget of 1,000 tokens across the board.
Okay, so 1,000 tokens for everything.
Right. For a simple algebra problem, that works fine. But what happens when the AI encounters the advanced calculus problem that genuinely requires, say, 3,000 tokens of scratchpad reasoning?
Ooh. It hits the 1,000 token wall, gets cut off before it can finish the math, and fails the problem.
Exactly. It destroys accuracy. The global budget overcompresses the hard problems, which basically ruins the AI's intelligence.
And I'm guessing it messes up the easy ones, too.
It does. It undercompresses the easy problems. If the budget is 1,000 tokens and the AI answers a basic addition question in 800 tokens, the penalty never fires.
Because it's under the limit.
Right. So the AI is still wasting 800 tokens on a problem that should really take 10. You simply cannot manually schedule a single limit that respects both simple arithmetic and advanced calculus.
So if a human programmer literally cannot guess the right token budget for every possible math problem, the AI has to do it itself.
That's the only way.
It has to become self-aware of its own learning process and adjust its priorities in real time. And that is exactly what the L8 framework achieves. Which brings us to the first major half of their solution, dynamic reward weighting.
Right. To untangle this whole mess, LED starts by changing how the rewards are processed. They use a technique called decoupled group normalization.
Decoupled group normalization. That sounds intense.
It sounds complex, but normalization is essentially just a way of putting apples and oranges on the same scale so you can compare them fairly.
Okay, so make sure one doesn't outweigh the other automatically.
Exactly. Instead of mixing the correctness reward and the efficiency reward together and then normalizing them, which causes that scale mismatch we talked about, lead normalizes them completely separately. The correctness scale and the efficiency scale are isolated.
Got it. That stops the length penalty from drowning out the math score. But the AI still has to decide when to care about length versus correctness, right?
Yes.
How does it actually know which one to prioritize at any given millisecond of training?
To solve that, lead introduces a mechanism called the potential scaled instability controller, or the PSI controller for short.
The PSI controller.
Hmm.
Sounds very sci-fi.
It really does. But think of this as a dynamic scale operating inside the AI's training loop. At every single step, it is calculating two specific metrics for both rewards: instability and headroom.
Okay, let's break those down. What exactly is it measuring when it calculates instability?
Instability simply means, is this reward still changing rapidly across the model's different attempts? If the model scores are jumping all over the place, it means the AI is still actively figuring this concept out.
So there is still a strong learning signal there.
Exactly. It's unstable because it's still learning.
And headroom.
Headroom measures how close the model is to hitting the absolute ceiling for this specific reward. If the AI is consistently getting the math right 99% of the time, the correctness reward has zero headroom left.
Because it has mastered that aspect. There's nowhere higher to go.
Right.
So the PSI controller multiplies that instability by the headroom and uses that number to shift the weights dynamically. Let's put this into a real-world perspective for a second.
Go for it.
It is very much like a teacher grading a student's essay over the course of a semester. Early on, the student rambles endlessly.
I usually do.
Right. So the teacher strictly grades the length of the essay. The AI is being heavily pressured to compress its thoughts. The efficiency weight is high.
Correct. At the start of training, the efficiency weight sits at around 0.5. The pressure to compress is intense. But as the AI learns to be concise, those answers shorten and stabilize.
And as it stabilizes, it loses its headroom. The PSI controller detects that the AI has figured out how to be brief.
Yep.
So, just like the teacher who realizes the student finally knows how to write concisely, the controller stops caring about the word count. It instantly drops the weight of the efficiency reward down to around 0.07.
Which is a huge drop.
Massive. It shifts almost entirely back to grading the actual quality of the math.
The AI has essentially created its own self-guiding curriculum. It applies compression pressure when needed, and then automatically shifts over 90% of its focus purely back to refining correctness.
And no fixed manual schedule could ever predict exactly when that shift should happen for millions of different parameters.
Never. It has to be dynamic.
Okay, so that solves the timing. The AI knows when to prioritize length, but that still leaves the second half of the problem.
Yeah.
How much length is appropriate for any specific question?
This is where lead completely abandons the idea of a global token limit. A flat 1,000 token budget, as we discussed, ruins complex reasoning.
Right, because calculus needs more room than basic addition.
Exactly. So instead, lead introduces its second major mechanism, per problem target length. They dynamically estimate a customized target length for every single individual prompt.
I think the paper refers to that as L star Q, right?
Yes, L star Q.
So it is calculating a bespoke budget for every single question. How does it actually determine that number? Like, how does it know how many tokens an advanced algebra question needs versus a geometry question?
It looks at the model's own correct answers.
Wait, really? Its own answers.
Yeah. Let's say the AI is given a difficult geometry prompt. It generates a batch of 10 different attempts to solve it. First, the LA framework filters out any attempt that got the final math wrong.
Makes sense. Discard the failures.
Right. Let's say 7 were wrong and 3 were correct. It takes those 3 correct trajectories, counts how many tokens each one used, and takes the mathematical mean.
Oh, I see.
That average length of the successful attempts becomes the new target length for that specific geometry problem.
Wow. And the framework enforces that target, using what they call a symmetric efficiency reward, which means it penalizes the AI in both directions, right?
Both directions, yes.
So if the target average is 1,800 tokens,
Yep.
and the AI rambles on for 3,000 tokens, it gets penalized. We expect that. But if the AI answers in only 500 tokens, it also gets penalized.
Which runs counter to what you might expect.
It totally does. Why penalize the AI for being incredibly fast? If I ask you a math problem and you solve it in 3 seconds instead of 3 minutes, I'd normally think you were just a genius.
But in the context of large language models, an oversort solution to a complex problem is a massive red flag.
Really? Why?
It almost always indicates that the model is faking it.
Faking it.
Yeah, it means the AI is taking a shortcut. It has likely just memorized the final answer from its training data, and it is pattern matching the output without actually performing the step-by-step logical reasoning.
And if you reward memorization, the AI loses its ability to generalize.
Exactly.
It completely loses its ability to reason through new, unseen problems because you trained it to skip the actual thinking part.
Precisely. By penalizing the AI for being too short, the symmetric reward ensures the model retains the precise amount of reasoning necessary to legitimately solve the problem. No more, no less. It forces the model to show its work.
But wait, there is a massive edge case here that jumps out at me.
Okay, what is it?
The entire target budget is based on averaging the length of the model's correct answers, right? What happens if the problem is so hard that the model hasn't figured it out yet? If it generates 10 attempts and all 10 are wrong, there are literally 0 correct answers to average. What is the target length then?
Oh, the paper handles this beautifully. This is one of my favorite parts. If there are 0 correct rollouts in the batch, LED assigns a sentinel value to the target length called B max.
The Bmax.
Yeah. This is the maximum permissible training length, usually around 4,000 or 8,000 tokens, depending on the setup.
Wait, so if the AI is totally confused, the system intentionally sets the target to the maximum possible limit?
Yes. If the model does not know how to solve the problem, LED deliberately backs off. It lets the AI ramble.
That's fascinating.
It gives the model a massive blank whiteboard to brainstorm on, prioritizing exploration and correctness above all else. It wants the AI to spin its wheels and try 100 different logical paths to discover a valid solution. It applies 0 compression pressure.
Until it finally cracks the code.
Exactly. The moment the AI finally stumbles upon a successful logical trajectory and produces at least one correct answer, the L*Q target length snaps into place.
Ooh.
It calculates the length of that correct answer, and the budget automatically tightens around it. Once the AI knows of the formula, the whiteboard is taken away, and it's forced to write the solution on a sticky note.
It is an incredibly elegant system.
Yeah.
But, as always, theory is one thing. Does this actually translate to better performance without lobotomizing the model?
It really does.
Let's look at the actual results from the paper, because the numbers really bring this home.
The researchers put LED through an absolute gauntlet. They evaluated it on 5 rigorous mathematical reasoning benchmarks, including the AM 2024 and 2025 competition problems, AMC, and Math 500.
Very tough tests.
Extremely tough. And they tested it using DeepSeek R1 distill models at both the 1.5 billion and 7 billion parameter scales.
Okay, let's focus on the baseline 1.5 billion parameter model. Before LEDA was applied on those AIM 2024 problems, the base model was using an average of 13,018 tokens per problem.
It was just talking in circles.
13,000 tokens. That is huge. But with the LA framework applied, it brought the average length down to 3,714 tokens across the benchmarks.
That is a massive reduction in compute cost. I mean, we're talking a fraction of the original length.
But length reduction alone isn't impressive.
Yeah.
I mean, older baseline methods, like one called shorter better, could also force the AI to produce fewer tokens.
Right. The issue was that those older methods caused the AI's accuracy to plummet because, as we discussed with the global budgets, they were indiscriminately cutting off hard reasoning.
But Elliott managed to slash the token count while actually increasing the average accuracy to 53.36.
Which is incredible.
It achieved the highest accuracy efficiency score, or AES, among all the reinforcement learning methods they tested, hitting an AES of 0.68.
And if you look closely at the data breakdown, it proves exactly why their dynamic per problem target works so well.
Also,
The researchers divided the test prompts into 4 tiers of difficulty, from Q1, which were the hardest problems, down to Q4, the easiest. The data reveals that LED doesn't just blanket compress everything uniformly. Compared to the older baseline methods, LED actually spends significantly more tokens on the hardest prompt tiers.
really, more tokens on the hard ones.
Yes. On the Q1 hardest problems, LED allowed the AI to spend up to 3,540 extra tokens compared to methods like GDPO or shorter better.
So it acts like an intelligent budget manager.
Exactly. It strictly rations tokens on the easy prompts, the simple arithmetic where the base model used to waste all its energy, and it funnels that saved budget directly into the problems that genuinely require deep, complex, cognitive heavy lifting.
While the older methods just blindly compress the hard problems, which destroy their accuracy.
Right. Lead spends its resources exactly where they are needed.
When you step back and look at this entire ecosystem, LUD has fundamentally altered how the AI operates. It is no longer a brute force calculator that just generates text until it hits a wall.
It really isn't.
It is actively rationing its own processing power. It deploys heavy compute for complex geometry and gives you a fast, snappy answer for basic algebra.
It marks a structural shift in reinforcement learning. We are moving away from models that learn think longer to think better, and entering an era of models that learn think exactly as long as necessary.
Think exactly as long as necessary.
I like that. And by dynamically balancing correctness with efficiency through the PSI controller and calculating those custom budgets via the target link estimations, LED achieves this entirely without a human holding its hand.
Which is huge. And for everyone listening right now, this is why a deeply technical paper on reinforcement learning directly impacts you.
It does.
This research is the foundational blueprint for how generative AI is going to scale. If you want a model that is smart enough to plan your entire vacation itinerary, but efficient enough to run entirely locally on your phone without draining your battery in 10 minutes.
Or costing you a massive subscription fee.
Exactly. This is the architecture that makes it possible. It's the end of the verbosity tax.
And allows us to shrink the operational cost without shrinking the intelligence.
And that leaves me with a final lingering thought for you to mull over as we wrap up today.
Let's hear it.
If an AI can learn to dynamically self-calibrate its internal quote-unquote thinking time based on how difficult a problem is,
Yeah.
if it literally develops a mathematical awareness of when it is making progress versus when it is just spinning its wheels, could this self-awareness of effort eventually lead to models that know when to just pause?
Pause. Like stop generating.
Yeah. Instead of wasting thousands of tokens and server compute guessing at a poorly phrased prompt, could the AI realize its own confusion, stop its internal generation, and simply ask you, the user, for clarification?
A model that understands the boundaries of its own cognition.
Exactly.
That is the logical next step.
We are getting closer to a world where when you ask the AI for the time, it doesn't give you the history of the clock, it just says 2 p.m.
And frankly, that is a future I think we are all ready for.
Absolutely. Thank you for joining us on this deep dive. We'll see you next time.